Okay, today we are going to make the second part of the lesson that is going to take us to the result of the torque of our rigid body and to be able to find the Euler equations. In the first part of this lesson, we showed this equation that I have here that will be useful in the next procedure. In this case, I switch some indices from this expression to this expression, which is the one that we are going to use. But it is, of course, the same expression. So what we are going to do is something very easy. We are going to take the Lagrangian of a rigid body in terms of the inertia tensor, and we are going to take that Lagrangian into the Lagrange equations, and we are going to see what happens. So, okay, remember that on the lesson talking about the inertia tensor and the kinetic energy of a rigid body, we found that the Lagrangian of a rigid body can be seen as 1/2 of the components of the inertia tensor jk times, well, the angular velocities minus, well, some potential energy, of course. So, and yeah, well, here we are assuming that the forces that are acting on the body, well, they are derivable from a potential, which is this B that I have here. Okay, perfect. So what happens if we take this into the Lagrange equations? So we know that these Lagrange equations tells us that 0 is equal to, well, the derivative with respect to time of the partial derivative with respect to some qi dot of the Lagrangian, which is this whole thing. And let me recall that this potential B depends on the generalized coordinates. Perfect. So let me take this into the Euler Lagrange equations. So this will be 1/2 ijk omega j omega k, and I'm not going to write this b here because it doesn't depend on the qi. So that means that the partial derivative with respect to qi dot is going to be 0. So let me write this as just this, and then minus the partial derivative with respect to qi of the whole Lagrangian. In this case, it will be ijk omega j omega k minus b, like this. Okay, perfect. So we need to take these derivatives. So this is going to be equal to the derivative with respect to time of, and pay so much attention in this. First of all, the inertia tensor components do not depend on the generalized coordinates of the system, so it will be a constant with this 1/2. So the ones that depend on the qi dot are the angular velocities, okay? And well, that means that we have the derivative of a product. So what are we going to get? This is going to be 1/2 ijk, and then times, let me take the derivative of the omega j with respect to qi dot times omega k prime plus, now omega j times the derivative of the omega k with respect to qi dot. Yeah, like this. And here's where we take the brackets close. Perfect. And here is going to happen something similar. These two functions, they depend on the generalized coordinates q, so that means that, well, we need to derive again a product. So that means that we are going to get minus 1/2 the inertia tensor components, the derivative of the omega j with respect to qi, omega k plus the derivative, omega j, the derivative of omega k with respect to qi, like this, and then minus, we have a plus, and then looking that b is a function of q, we just express the derivative of b with respect to qi. Perfect. Okay. Let me tell you something. Remember that the inertia tensor is symmetric. So that means that I can switch this j with this k. I can switch these indices. And this inertia tensor is multiplying this term and this term. So that means that I'm going to have two inertia tensor components. Let me write it. It will be something like this. Let me put the parenthesis here, plus ijk. Okay, I think that's correct. So, look something. I can switch this k here and this j here. And then I need to change these indices here. But remember that the inertia tensor is symmetric, so that means that that doesn't make a change. ijk is the same as ikj. So that means that I can just switch these two indices without any problem, and nothing changes. And that is to be able to have the derivative of the omega k, which is the same thing that I have here. So in other words, what we are going to have is 2 times the inertia tensor times the derivative of omega k times omega j, because it is the same in this term and in this term. So we sum these two terms. So we are going to have here the derivative with respect to time of 1/2 of 2 times the inertia tensor jk, the derivative of omega j with respect to qi dot omega k, like this. Perfect, if we sum these two terms. So, yeah, we can cancel these 2's, and we get this. And then, here in this other part of the equation, we are going to have something very similar, but now we are taking the derivative with respect to qi, but it's just the same. So we are going to get that this can be seen as, well, 2 times the derivative of omega j with respect to qi times omega k, like this. So we will have minus 1/2 the inertia tensor components jk, 2 times the derivative of omega j with respect to qi omega k prime, plus the derivative of b with respect to qi. Perfect. Again, we can cancel these 2's. And finally, well, we are going to get the derivative with respect to time of the inertia tensor jk omega k, the partial of omega j with respect to qi dot, minus the inertia tensor jk omega k, the derivative of omega j with respect to qi, plus the derivative of v with respect to qi. Okay, and remember that this is equal to 0. And what we have seen in previous lessons is that, well, we know that the angular momentum, a component of the angular momentum, the jth component in this case, well, it can be seen as the inertia tensor jk omega k. Yep, we know that we can calculate the angular momentum in terms of the inertia tensor and the angular velocity. Actually, we have a lesson which is named as angular momentum in rigid bodies, where we use this expression. We explain further how to get to this expression. So that is what we are going to use in this case, because you can see that here we have this, and here we have this. So that means that this is equal to the derivative with respect to time of the angular momentum times, well, this derivative of the angular velocity with respect to qi dot. But here's something that we can do. Also remember that we used another expression where we introduced the function m, yeah, the function m. On a previous lesson, we established that the angular velocity omega s can be seen as a function m sr qr dot, where m is a function of the generalized coordinates. Again, this was shown on the previous lesson, the first part of this lesson. So, if we analyze this expression, well, it is very easy to notice that if we take the derivative of omega with respect to qi dot, we are just going to get this m. Because taking the derivative of this with respect to the qr, well, it will cancel this qr and we will only get this term. So that means that if we have the derivative of omega s prime with respect to qr dot, well, we get msr. But here we have the derivative of omega j with respect to qi. So that means that this will be an m, but with the indices ji. Okay? Perfect. So let me move this maybe here. I don't know. Yeah. So then we have minus. Again, we have the jth component of the angular momentum for this expression, and then we have here the derivative of the omega j with respect to qi. But remember, again, this omega can be seen as this expression over here. So this will be equivalent to omega j prime equals to mj prime iqi dot. So what happens if we want to calculate this partial derivative that we have here? Well, the partial derivative of omega j with respect to qi, well, looking at this qi dot doesn't depend, of course, in the qi, it's a constant, and this function does depend on the qi, so that means that we are going to just express the partial derivative as it is. So we are going to get something like this: the partial of mji with respect to qi, yeah, qi dot, but okay, of course, you should notice that we are taking 3 times the same index, so this is wrong, and that is because we are naming with the same index the variable we are taking the derivative with respect to, and the index that we are using here to define the omega j. So that means that we may need to change this one to a k. And then we take the derivative with respect to qi, we switch this for a k, and nothing happens. Okay? So we can write that this angular momentum is multiplying the derivative of mjk with respect to qi, and then qk dot, and then plus the partial of b with respect to qi. Okay, remember this is equal to 0 due to the Lagrange equations. Okay, perfect. So now, well, we need to calculate this derivative with respect to time. So this will be equal to the derivative of the first variable, like this, times the second variable, and then plus Lj prime times the derivative with respect to time of this m. Remember, again, this m is a function of the q's coordinates. But these q's, well, they are functions of time. Okay, so if we need to take the derivative with respect to time of the m, well, we need to use the chain rule. Like this, the derivative with respect to time of mj prime I is going to be equal to first the partial of m with respect to q, and then q dot, which is the derivative of q with respect to time. So that is the rule that we are going to use. So if we do that, what we are going to get that this will be the partial of mji with respect to, let's say, qk, and then qk dot. Perfect. Minus lj, the partial of mjk with respect to qi times qk dot plus the partial of b with respect to qi. Okay, perfect. So, as you can see, we have a common factor lj here. So we are going to take that out, and actually another common factor qk dot. So we are going to get that this is the derivative with respect to time of lj prime mj prime I, and then plus lj prime, which is going to multiply the partial of mj I with respect to qk dot minus the partial of mjk with respect to qk dot plus the partial of b with respect to qi. Perfect. And as you can notice easily, this expression is the one that we found on the first lesson, which is this. Okay? So we are going to copy this quantity and to replace it on the equation that we have here, like this. And this will be the derivative with respect to time of lj mji plus lj that multiplies this. Well, it also multiplies a qk dot plus the partial of b with respect to qi. Perfect. So this is equal to 0. Okay, well, we are about to get to the important result. By now, we are going to switch this j for an r, which is also going to change this j for an r. Yeah, remember, nothing changes. It is just a change of indices, just to be able to match this m with this m, okay? To be able to have mri as a common factor. So if we do that, let me change it. Yeah, if we take the mri as a common factor, we are going to get mri, which is going to multiply the derivative with respect to time of lr plus lj ersj mskqk dot plus the derivative of v with respect to qi equals to 0. And as you can easily notice, this term that we have here can be expressed in terms of the angular velocity. Remember the equation that we showed at this part of the lesson? We can write this in terms of this. So we can substitute to take this out to get omega s prime like this. Perfect. So another thing we can do is to take this partial derivative to the other side of the equation, and this is going to be equivalent to minus the partial of b with respect to qi. So let me put an arrow here. And what other thing can we do? Well, again, remember that when you use the index notation, well, this can be easily associated with the elements of matrices, looking that we are using two indices. Okay, so in this case, all these elements M, well, they represent the elements of a matrix M. So that means that, well, this can be seen as a matrix equation, maybe. And what we are going to do is to, well, take the elements that represent the inverse of that matrix M, and we are going to multiply on both sides of the equation by those elements of the inverse matrix, to be able to take this element to the other side of the equation. So that is what we are going to do on the next step. Perfect. So if we do that, we are going to get that the derivative with respect to time of LR plus Lj ER J omega S is equal to, well, minus those elements of the inverse with the indices I, R, times the partial of B with respect to Qi. Remember that this matrix M, it has to be an orthogonal matrix. So look that here I'm taking the transpose matrix. That's why I switched the order of the indices. Because when you have an orthogonal matrix, remember that the inverse is equal to the transpose. So that's why I switched the indices. Okay, perfect. Yeah, so what we need to define here, which is going to be the important part of the lesson, is that this term that we have here is going to be called as the earth component of the torque of the rigid body. Okay? Yeah. So that is what we need to define to be able to establish the equation that tau r prime is going to be equal to the derivative with respect to time of the angular momentum components plus Lj ERS J omega S. So what is this telling us? This is telling us that we are able to find the torque of the rigid body in terms or with respect to the fixed basis on the rigid body. Okay? And that depends on the angular momentum that is also expressed in that basis, and, well, this product that involves the angular velocity and the angular momentum components. Okay, but remember, it is important to notice that this is the torque prime. Again, this is with respect to the basis that is fixed to the rigid body. Remember that we had the rigid body and we fix a coordinate system to a point of the rigid body, which will be moving with the rigid body all the time. Okay, so this basis, this coordinate system is always going to be on the same point. So that that is what I mean, that we are calculating the torque with respect to this coordinate system. Okay, perfect. And well, what we are going to say now is that, well, we remember that from our initial courses of physics, well, we are taught that, well, the torque can be calculated as the derivative of the angular momentum with respect to time. Okay, maybe like this. And, well, we have seen on previous lessons is that remember that we had another coordinate system that was an inertial frame that was only static. It doesn't move with the rigid body. So there was an equation that relates the angular momentum measured with respect to this coordinate system in terms of the angular momentum measured with respect to this coordinate system. And that equation was very easy. It was that the ith component of the angular momentum in the, let's say, natural coordinate system is equal to AIR prime, LR prime, where of course these are the components of the angular momentum with respect to the fixed coordinate system. Okay, so what happens if we take the derivative with respect to time to get the torque with this equation? Well, we get that the Li dt is equal to, well, the derivative with respect to time of these two quantities, but that is going to be, well, AIR, the derivative of LR with respect to time, plus LR prime, the derivative of AIR prime with respect to time, and this is equal to AIR prime, the derivative of LR with respect to time, plus LR, plus, well, this can be seen as AIR prime dot. And we have an equation that we have been using in these lessons to represent this element in terms of the angular velocity. Okay, that expression is this one that I'm writing here. ERKS omega S AIK. Perfect. So we can substitute that result. Let me erase that plus sign. Yeah, to get that this is ERKS omega S AIK prime. And as you can see here we can switch the R for the K in order to be able to have the same common factor AIR. So we are going to take this K to get an R, we take this K to get an R, we take this R to get a K, and this R to get a K. So that allows us to write AIR prime times the derivative of LR with respect to time plus LK EKRS omega S, like this. So what is this telling us? Remember, the famous formula tells us that this is the torque I, that corresponds to the measure made in this coordinate system. So we are getting that this whole expression that we found, that was defined as the torque, well, the rth component of the torque with respect to the prime basis. Well, that means that the torque in the natural basis is equal to AIR prime tau R prime, like this. So this is telling us that the torque is transformed the same way the angular momentum is transformed, like using these A's that correspond to the transformation matrix A, which is the transformation matrix that takes you from this coordinate system to this coordinate system, and the inverse matrix takes you from this coordinate system to this coordinate system. That is what the matrix A does. And that matrix A is also useful to transform the angular momentum, and now we have shown that it is also useful to transform the torque of the rigid body. And something that I forgot to mention is that at this step, these are known as the Euler equations. I have been saying all the time that the important thing here is to deduce the Euler equations, and I forgot to mention that the Euler equations are the ones that are given with this expression that we found recently, which is an expression to find the torque. So yeah. Okay, and this is the result that I wanted to achieve. This will be the the end of this lesson. Just remember, these are the Euler equations, and this is an equation that relates the torque measured in the natural coordinate system and the torque measured with respect to the fixed basis on the rigid body. Perfect. So this will be a good place to finish the lesson.